Okay, I think we can start with the course. And first of all, my name is Pedro Ojeda. So I'm working as an application expert at HPC2N. And one of our tasks is to deliver this type of training courses. And today we will talk about basic molecular dynamic simulations. And after that, we will see how to implement a QMM setup using our result from molecular dynamics, right? We have chosen some specific software for this course, and this is by far the only software that you can use for QMM simulations. There are other type of schemes, and sometimes it depends on the research community where you are working on. And depending on that, then you can be more close to some particular software. So for today, we have chosen a VMD combined with NAMD, because these two particular software can work very well together, and actually they were created to work in this way, in a synergistic way. And later on, the developers realized that not all the problems can be solved with the classical MD, and that's why they decided to create an interface for QMM simulations. And the approach that they use is that they use basically a scripting format, so that you can use your preferred quantum chemistry code. Today we will see how to work with Gaussian and Orca, and these are only two particular software that you can use. And these were chosen because basically they are installed already on Kebnekaise, so you won't have to deal with the installation, which sometimes is a bit tricky, right? So I will show you how to work or to do the first steps with this software. As you will see, there are different options that you can use in molecular dynamics, classical, and besides that, we will be adding more options, right? When we look at the quantum mechanical part. So again, this won't be an extensive lecture, an extensive course on how to deal with specific options. Rather, it will be an introduction on how to use these combined packages, right? And I will leave you with more questions, more likely, and that you can then solve. And of course, I will be there if you have additional questions that are not covered in this particular course. So let me share my screen. And as Brigitte mentioned before, she will be assisting us with the course today for the system part. And let me increase the font size. What is it? So this is the agenda for today. We will start with the lecture on classical MD. Then we will look at one particular example of how to set up a molecular dynamics simulation using a plugin from VMD, which is called Quick MD. After that, we will see how to set up a classical MD simulation, but using the pure command line, which is the TK terminal from VMD. And after lunch, we will start looking at the quantum mechanical part, right? And then we will use Orca and Gaussian, which are standard codes for quantum chemistry. So the material will be recorded. So you got a document where we mentioned that we have additional shared documents for one is for questions and answers. And here I will try to reply as soon as possible. And yes. And here in the other document, we have the important information on the course where you got most probably the link for the Zoom and the location of the Git repository and other instructions, right? In the GitHub repository, you will see two setups, one which says Orca and the other Gaussian, and they start with the basic MD simulation, and then we add a QMM layer. In the lectures part, you will find the two PDF for the lectures of today, one for classical and the other for QMM. You can look at the presentations here online, or you can clone them and get the lectures. So basically, we will work with this repository when we start with the examples. Right now, I will go to the first lecture. So can you all see my presentation? Yes, good. So let me start with the classical MD simulations. So first of all, I added this slide because before I started working in this field, I thought that the name molecular dynamics simulation was quite new, right? But actually, it dates back to the 1700s when Isaac Newton found this force law. And in particular, in the case of the gravitational force, we know that it involves the interaction between two objects. In particular here, it's the attraction of the apple to the earth, right? So, and this is expressed in this force term here, right? So molecular dynamic simulation is not that new. Actually, it's not new, but the difference is that now we have better algorithms to solve these equations and also better hardware, right? We have now, for instance, GPUs that can compute 1,000 of arithmetic operations or million of arithmetic operations per second. And here, if you see, this is just one particular force that can be computed. And as I mentioned before, is between two macroscopic objects, in this case, the apple and the earth. But we can also put that in terms of atoms, right? And that's what we will see today, because the atoms can be modeled as objects, as basically as balls. So the Newton's law, we have this equation: the force is equal to minus the gradient of some energy function, which is also called the Hamiltonian, right? So in order to solve this equation, because it is a second order derivative equation, we need two conditions. And in particular, we can pass the positions and the velocities to this equation. So everything will be deterministic if we could specify the positions and the velocities of the particles just at the beginning, and then everything will be solved by using this equation, by integrating this equation here. So the problem is that in nature, in a realistic system, this value n here is quite big. For instance, it's of the order of 10 to the 23, right? And it's impossible to get the exact positions and the exact velocities of all the objects involved in a realistic system. And previously in the Newton's times, they were concerned, for instance, just in solving this equation. What is that? This equation here, and for the gravitational force between two objects only. Now, and now we want to solve this equation for 1,000, even for million of particles. So, as I said before, the algorithms that we have now are better suited for this type of equations. Okay, the function that I mentioned before, this U here, can be seen as a landscape, and here I put the analogy with a landscape in some terrain, right? And we can see different type of hills and also valleys. And imagine that you are at one of these points in this landscape. You start from this point here, and you want to know, or to to know all the places around this landscape. So what you can do is you can start with some trajectory and then move around. Sometimes it will be hard because it's a hill. This is a steep path, and that will be difficult to reach, right? But other times it will be lighter because it's a valley and the terrain is flat, so you can go and do your sampling, so to speak, right? And this is basically what the atoms are trying to do in molecular dynamics. They are trying to reach all the possible conformation or states in your simulation. And sometimes it's hard because there is an energy barrier that they need to overcome. And if the conditions are not appropriate, they won't be able to sample that region. In the molecular dynamics terminology, this can be called the conformational space, right? and the energy is a function of the conformational space. So besides the fact that molecular dynamics started in the 1600s, basically, so only very recently there appeared some hardware and new algorithms to integrate the Newton's equations for more than 2 particles or a few particles. Here, for instance, I show you some early works on MD, and in 1957, there was a simulation for a hard sphere system. So basically, balls that cannot penetrate each other. And I also found this work on the motion of atoms in liquid argon, right? So argon, it's a quite a simple system right now, and sometimes it's used to test that our molecular dynamics code works fine. Going ahead, we found this paper, which is on protein folding using a conformational computer simulation. And this dates back to 1975. And this was from Michael Levitt and Ariel Waschel, right, who later on received the Nobel Prize. It also shared with Martin Karplus. And it was for the development of multi-scale models for complex chemical systems. So multi-scale model, this is something that we will see today because we will use a different type of schemes to treat a certain system. In particular, we will see the classical and quantum mechanical. So here I put how I see now the synergies between experiment theory and simulations. So I remember that some years ago, if you submitted a article talking about experiments, then it was fine, for instance, in the field of biomolecular simulations. But now sometimes the reviewers ask you, if not always, ask you for a simulation or some theory to back up what you are saying in the experiment, or the other way around, right? So also, this is just one view, but it's also true that even when we have our very good theory or our nice simulation results, we always need to back up these results against to the ones in the experiment, right? This one experiment gives you the last word. So these are some possible systems that can be treated with molecular dynamics. In this case, I show you an enzyme in water. So these little things here are water molecules. And the spheres are the ions, and this monster here is a protein, right? And inside the protein, there could be some small molecules, also called ligands, right? And this can be solved in molecular dynamics. This is very standard, but now there are other systems where people are applying molecular dynamics as well. For instance, here, this is a clay system. And one expert here in Umeå working on clays and molecular dynamics is Mikael Holmboe, who works in chemistry department. In the case of adenylate kinase enzyme, we have also experts at Umeå University. For instance, Magnus Andersson or Magnus Bolpatz, who works also at chemistry. We have also other people working in molecular dynamics at Umeå University. So this is another interesting result, and this, you see, it's on ice cream, and some people are using molecular dynamics to study systems that are very difficult to deal with in the industry, right? In the civil engineering area, there is also potential applications like this here with asphalts. So asphalts are challenging because they are a matrix of different compounds, and one needs to do some realistic simulations on these systems, right? So now let me go to some equations. The U that I mentioned before for the force computation, it's called the energy, or the Hamiltonian in this particular context, right? So in molecular dynamics, we have many terms for this energy. In particular, we have some term for the bonds, the angles, the torsions, and the coulomb. And these terms here will make the difference between the force fields that you choose. There are several force fields. I will talk about that later. And basically, they will differ in how these terms and also these parameters, for instance, K bonds, K angles, and so on, how these parameters are treated. So this is a illustration of the different terms. We have, for instance, the bond length between two atoms and also the angle, right? And they are modified by these hyperparameters. K bonds are 0, K angle and theta 0. We have also the torsional angle that involves some dihedrals, right? The Lennard-Jones parameters, which are modeled by this type of function here, which is also called the 12-6 term, right? So in the Lennard-Jones, we need to define a parameter called epsilon, and also the sigma parameters for the radii of the atoms. So notice that in classical molecular dynamics, the atoms basically are balls. It's like having two balls and make them interact. So here is a comparison of the different force fields or some of the force fields that can be found in the literature. We find the charm force field, and there are different versions of this force field, starting from the 22, and now it's going to the after today, it's going to the 36 version. And there is also the OPLS force field. There should be the also a Gromos force field. So the main difference with the charm force field is that in this energy term, there is an additional term for accounting for the more precise Ramahandran plots, right? For the dihedral angles. So charm is a well-established force field, and this is the one that we will use today. So now let me go to a very simple energy function. The one that I showed you before had several terms, the Lennard-Jones, the bonds, angles, but imagine that you have a very simple equation for the energy. In this case, it's just a sinus times a cosine. And here you see that this plot here is very rough. So it has many minima and many maxima, right? And this is just a very simple equation, right? But imagine the one that I showed you before with several terms. We expect that it should have more minima and more maxima. And imagine that you start here as a walker, or your atoms start here, and they want to go to a different minima here. Then they need to overcome this energy barrier. And if, for instance, the temperature is not appropriate, or the conditions are not appropriate, then they won't be able to get to this region here. And that will be a problem, because in molecular dynamics, to get precise and accurate results, we need the system to know everything, or most of the surface, the energy surface that it is exploring. So here there are some force fields for proteins and hydrocarbons. We can use chromos or PLS, amber, charm. For clays, there is a clay force field, and coarse-grained Martini. I will talk a little bit about the Martini later on. If the parameters, this is very important. So if you are considering some system that it was well studied previously, and the parameters for your system are known, then there is no problem. You can use your force field, right, as it is. But in most of the new or realistic systems, you will need to add something or some more information into the parameters. For instance, imagine that you are dealing with a new clay system, right? Or you have a new amino acid, a modified amino acid, for which the parameters are not known. In that case, you will need to go to quantum mechanical approaches or the experiments, and then set these new parameters into your force field. Dealing with a force field parameterization, it's kind of an art, right? It takes time. It's not sometimes easy to do and to validate. Yeah? But if you have a system for which the parameters have been already tested, then you can go and use it. So these are some models for waters. Water is very important in some systems, for instance, in spectroscopy. And the quality of the water will depend on the model. Here we are seeing the so-called three sides model, because it involves only 3 atoms. We can also have an additional auxiliary atom, which corrects for a dipole moment, and a more precise model, which involves 5 sides, 5 atoms. But of course, your simulation will get slower if you use this model rather than this one, because water is the major contributor in a simulation. In a protein simulation, for instance, most of the system is water, and if you add two more atoms per molecule, that will be a larger system or a heavier system to simulate. So, but it should be more precise. It depends on the type of calculation that you need to do. So in a particular system like a protein, we have 20 so-called amino acids in nature. And this is where I mentioned the modified amino acids before, because sometimes you need to add something to the natural amino acid. The parameters for all these 20 amino acids have been well studied, and we can use that. But there are some amino acids that sometimes become modified, and then the parameters are not known. So today we will use the natural amino acids. So a good source of information for proteins is a protein data bank, where you can see the structure of the protein and also the sequence and several motifs that can be found here. So going to the field of molecular dynamics, we can see that in our particular case, initially, what the people simulated was a small system, right? Imagine that you have some atoms, right? And then we can run the plain Newton equations, integrate them, and propagate the dynamics. So, but if you simulate in a computer like 1 million atoms in your simulation, this is still not a realistic system, because in a realistic system, the number of particles is around 10 to the 23, and that's not comparable to even 1 million particles. So in order to avoid this issue, so in molecular dynamics, you can use the periodic boundary conditions, where you have a main cell consisting, for instance, of the billion of atoms, and then you surround that with copies of the cell and let them interact. So there will be, for instance, some radius where the particles can see the other particles from a different cell, and this will be called the minimum image convention. This is the system of protein in water. Sorry if I speak only on proteins today. This course is about simulations of biomolecules, where I have more experience. There are also, as I mentioned before, people in Umeå that are working on clays and other systems. But the exercises that I will talk about today are mainly with proteins. The ideas are similar in other systems, or of course, but the main difference would be the setup, right? Because for biomolecules, there are already several tools to set up the system, and also the parameters. So one important component in the molecular dynamic simulations is the long-range interaction part. specifically the electrostatic energy, because when we use a periodic system, we get this type of summation for the energy term. And then it seems that this summation is not well defined if you don't use the correct scheme for the summation. So it depends on how you do the summation here. So it's quite tricky to do this energy computation. And there are several methods to solve it. And once all the energy terms have been computed, we can add them into this energy term here. And then we can do the integration. This is a second order equation, as I mentioned before. And we can integrate that with different algorithms. And here I show you the leapfrog scheme, where you compute the velocities at the middle of the interval, and then you add them to the positions and update the positions and do something similar to the velocities. In this way, you can propagate the dynamics. And for a realistic system, or for solving the system you have in hand, you can use the idea of ergodicity, where you can take the sampling over the conformations that you get as an approximation to the sampling in time, right? So this theorem is based on the idea of equilibrium. And here I put a picture of my coffee cup. So, but of course, this idea is based on equilibrium, and this cup is not in equilibrium. But what I meant with this picture is that the system that we are simulating should be large enough, right? So previously we saw the conformational space, and imagine that you want to monitor some property in this Bailey, like for instance, the number of trees. So what we need to do, we can take some random points across this energy conformational space, and then we can say, well, here there are 2 trees, and here there are 5, and so on. And we can say at the end, well, the average number of trees is given as the average of the samples that we took. But also we can propagate or go through trajectories. We are start here, not randomly, but and go across this landscape and monitor at some steps. How many trees are here? 5. How many trees are here? 8, and so on. And go ahead and look for how many trees there are. So that would be more time consuming, right? But if the sampling is not correct, or we cannot reach this point, for instance, we won't get information on this part. And maybe if we can sample here, we will say, oh, here there are 100 of trees. And we will get the wrong idea that the average of trees is 100. But we haven't seen what is here because there was a height barrier. And that's the idea of the ergodicity theorem, right? That if we don't sample enough and well, then we won't get any trustable results. So there are different type of ensembles to compute the thermodynamical properties of the system. And here there is more math. In particular, we have the microcanonical ensemble, where the number of particles, the volume, and the energy is conserved. And the canonical ensemble, where the number of particles, the volume, and the temperature is conserved. We have also other specific ensembles that can be used, for instance, if you fix the number of particles or you change the number of particles, right? The important point here, or the message, is that for all these ensembles, we need the so-called partition function, right? Because with the partition function, we can compute all the thermodynamical properties of the system. In this case, this is the partition function for the MVE ensemble. This is the partition function for the MVT, and there are other type of more specific ensembles. So there are some ways also to keep the constant some the properties of the system. For instance, we can keep constant the energy, we can keep constant the temperature, or the temperature, the volume, and the pressure, right? And for instance, in MPT, with a constant pressure, this can be simulated with many type of thermostats. For instance, Berendsen and Parinello-Raman, right? So in molecular dynamics, we have many atoms, right? Maybe millions of atoms. And if we use a single machine as a laptop, for instance, we do our coding, we prepare our program, and it runs well. We test it, it conserves energy, everything works, right? So the problem could be if our machine has only one CPU, and imagine how long it will take to compute a single energy calculation, right? A single step. So that will be a long time. But imagine that instead of that, we divide the problem. So as in the case of this cacher, the line was very long because there was only one cacher. But if we put 3, then we can divide the work, right? And it's the same with the molecular dynamics, because in that case, we can use different CPUs to compute or to divide the work of the integration and energy computation among them. And that will reduce the total time for the execution. And this is the parallel computation that is now applied in most of the molecular dynamics code. This also helps us because we have already decreased the work that one single CPU, in this case one cache, can do. Then we can increase even further the size of the system, and then we can deal maybe not only with 1 million atoms, but we can deal with 10 millions or even more, right? So the cluster that we will be using today is Kebnekaise, which is at HPC2N. And this is a nice picture that we took some years back. And basically, what happens in this type of clusters, we have several nodes, and these nodes can communicate with each other, right? There are some protocols for doing that, and one of them is called the MPI, Message Passage Interface. And the point is that inside each node, we also have a different type of architecture. And in this case, you can see that inside one node, we have different number of cores. And these are the CPUs that will be solving the Newton's equations. For instance, here, this is a pseudocode where I am doing a loop over the particles, and then I'm updating the position based on the forces that were computed previously. And each of these single computations will be solved by all of these cores here, right? In particular, on Kebnekaise, we have 28 cores per node. And you can also scale your molecular dynamic simulation up to many nodes, as is shown here. So there are different schemes to parallelize the code. You can do the pure MPI parallelization for parallelizing across the nodes. Also, you can implement the MPI plus OpenMP to optimize the memory locally, and also using different algorithms like the main decomposition and several other techniques. These techniques can be applied to speed up your code that initially started running on a single CPU. So another technique to speed up your simulation is by using the so-called coarse graining. And this is where the Martini force field comes into play. And here I show you the representation of a protein by using balls and sticks. And in the Martini force field, what the people try is that they reduce the number of atoms into a single bit with different properties. So as you can see here, the total number of particles decreases completely, right? And this makes the simulation faster, and that's why you can do a longer simulation with the Martini force field. The problem can be in the accuracy of the results. And currently, at least for biomolecules, the Martini force field is becoming more stable, because I remember when it started, it had some issues, but they have been solved over these years. So this is a potential application for coarse-grained simulations. So imagine that you have some system like these fibers here, and each of these fibers is represented by a ball, right? But if you wanted to simulate each ball, then it will look like this. And each of these sections here is composed of a huge protein. So it would be impossible to simulate this type of system by using the molecular dynamic simulations that we will see today. So Martini and coarse-graining is a good option for very large systems. So yeah, here I present you a time scale for the different type of modeling approaches. And this is by far the most complete plot that you can find. But this is how I visualize the different type of simulations. So in the literature, you can see that there are ab initio simulations, also classical molecular dynamics, and this is what we will explore right now, or we are already exploring. And with these simulations, you can consider millions of atoms, right? In this scale, millions of atoms. And also, you can do some sampling to the nanoseconds or microseconds simulations. And in this time scale for nanoseconds and microseconds and larger, you can detect some conformational changes of biomolecules, for instance. At the bottom, we found the ab initio simulations, and the time scale that these simulations can achieve is in the order of femtoseconds. And basically, this is the order of the bone vibrations, right? So, but the difference is that these simulations here are very accurate, right? And they can model systems that cannot be achieved with classical molecular dynamics. So in the middle, we have different combinations or mixtures or hybrids of these two. We can find, for instance, semi-empirical methods for solving quantum mechanical systems. And this can achieve in the order of picoseconds time scale and nanoseconds even. So in the different time scales, we have bone vibrations, bone isomerations, water dynamics, and conformational changes. So software for molecular dynamics, I always find new software. Yeah, when I think that I have seen most of them, I find one more in the literature. And this is quite good because this field is very robust. And here, for instance, we find the NAMD, GROMACS, AMBER, OpenMM, CHARM. So most of them are quite fast, very well optimized, and also for modern architectures. The purpose of this software is different, and in particular, this software that I mentioned today is for biomolecular simulations. For other systems like clays and other systems that are not from computational chemistry or computational biology, then you can use a different software. Maybe is more suitable because they have other tools for dealing with that systems. So I will talk today about NAMD mainly, but the other software are also well optimized, and most probably you can use QMM approaches as well. So basically, in an MD simulation, I follow these steps. First, set up the system, then a minimization to avoid the atom clashing. After that, a solvation, neutralization, equilibration, production, and analysis. And of course, this step, minimization, can be combined with all these steps, right? If necessary. So here there are some references for molecular dynamics. They are classical and quite compelling. So I think this is it for the first lecture. Do you have any questions at this point?
There is a question in the Q&A document.
Okay. So I will stop sharing because I cannot see my documents. Let me see. Questions. Okay, there is a question and I will read it. So it says, how do you decide which force field to use for a specific application, enzyme, ligand versus protein? Are there any guidelines or is just experience or personal preference? So I will say that basically the existing literature on the force field is the first source, right? Because in the existing literature, you can find how the force field was applied, right? And if it works. For instance, I showed you previously a benchmark that was done with several force fields, including OPLAs and CHARM. And then you can see if the force field somehow reproduces the chemistry that you're trying to simulate, right? Basically, the literature and how well it behaves with similar systems. But this is also a challenge, right? Because sometimes in the literature, a force field is reported for the best results in some system, but then you try your own system with your own characteristics and it results that it reproduces, another force field reproduces better the experimental results. I have seen that in membrane systems in proteins, right? Because CHARM is a well-established force field, and but depending on the setup or the molecules that you are using, that could vary. So literature is the first step that I would personally check, right? And then check against the experiments and, of course, the knowledge you have on your system and the chemical intuition that you can provide. Is there any other questions? At any point, you can interrupt me and ask me and tell me why I have this opinion. I think I am not an opinionated person, but sometimes, of course, I express the opinions, and it's good if you ask me, why do you think like that or so on?
But remember, if you do talk in the lectures, it might get recorded.
Oh, I see. I
I
see.
guess you can
I
ask
see, yeah.
you can ask in the Q&A document, or for that matter in the chat. If I see it and if it's something important, I can ask the question for you. Then
That's a
if you
good
care.
idea. Yes, that's a good idea, Benita. Thank you for that.
Of course, if you don't mind being recorded, I mean, then you can just ask.
Also, in this course, you will see that there are parts that most probably you already know, but sometimes I will go faster, so it depends. So please let me know if I can clarify something or I can extend some part.